This is our video 5 on energy and work, and most of the questions here are going to be spring energy related, but at the end I have just potential and kinetic energy conservation of energy problems. So let's look at this question. I will also introduce the power in this video. So at the end, last 5 minutes or so, we're going to have a power question. So we have two blocks are connected by a light string that passes over a frictionless pulley as shown. The block of mass M1 lies on the horizontal surface and is connected to a spring of force constant K. The system is released from rest when the spring is unstretched. If the hanging block of mass M2 falls a distance h before coming to rest, calculate the coefficient of friction between the block and of mass M1 and the surface. And you see that none of the numbers are given, so you don't have in this question any numbers, so it's all formula deriving. And a lot of questions on AP exam are going to be like this, where you don't have numbers, you have to derive formulas. So when I look at this system, I say right at this moment, the block has potential energy. So the block 2 has gravitational potential energy. And by the time the block gets to the bottom, that potential energy is going to be equal to 0. And then it will move this distance h. So it moves the distance h. Then that means this block is also going to move the distance h. So this stretch is going to be h. So I have the gravitational potential energy of the block 2. So the gravitational potential energy of the block 2, that's what I have before it got stretched. And afterwards, oh, by the way, not all the gravitational potential energy is going to go to the potential energy of the spring. So because when the block loses all its potential energy gravitational, the spring is going to have potential energy because it's going to be stretched. But not all the potential gravitational energy is going to go to the spring energy because there is friction. So this energy minus the work done by the friction on the block, so friction on the block 1, and the rest is going to go to the potential energy of this spring. So I'm starting with potential energy of the block 2. I have M2GH minus the friction force on the block. It's mu times N. And N of the block 1, you have the normal force up and the M1G down. So the normal force for the block 1 is M1G. And the distance is going to be H because that's by how much the spring is going to be stretched. And that is going to be, wherever is left, is going to be potential energy of the spring. So that's going to be 1/2 K. And x squared, in this case, x is still h. So it is h squared. And what I see here is that every single one of them has h. So I have h here, and I have h here, and I have one of the h here that I can cancel. Then I'm going to multiply every single one of them by 2 to get rid of the fraction. So I have 2m2g minus 2 mu m1g and equals to KH. And I am solving for coefficient of friction. So I'm going to move my coefficient of friction term to the right and KH to the left. So then I will have 2 mu m1g is equal to 2 m2g minus KH. So mu is going to be equal to, and we don't have numbers, so we don't have to solve any further. So we have 2m2g minus kh minus, and divided by 2m1g. So this is our final formula for the coefficient of friction for this question. And just to go over it again, I started with the potential energy of the second block. That's how much energy the system had. The first block has no energy because the spring wasn't stretched. Then after the spring stretched, not all the energy that the potential gravitational energy that the block 2 had went to the spring energy, because some of the energy was stolen, like the tax guy was taken away by the work done by the friction, and the rest went to the spring energy. So you always have to look what you had before, if anybody is gonna take it away, and the rest is gonna go to the spring or whichever is happening in the problem. Here's another question we're gonna look at. A mass of M equals to 1 kilogram starts from rest and slides a distance d down the frictionless incline of angle 30 degrees. While sliding, it contacts the unstretched spring of negligible mass as shown. The mass slides an additional distance of 1 centimeter and is brought to momentarily to rest by compressing of the spring. The spring constant is given 2400 newtons per meter. Find the initial separation d between the mass and the spring. I'm gonna assume that this whole thing is gonna be the compression, even if it is not the compression. Let me show you this right here. So even if it is not the compression, so the block starts here, and I'm gonna say it has the potential energy, and here is the spring, and it will only compress by this much. So I'm gonna say this is where the potential energy is gonna be equal to 0 gravitational, and this is the maximum mg and h, and this is gonna be my h. But the spring could go any further, but I'm just gonna look at the triangle that involves only the motion of the block. So again, before I start the question, I'm gonna say, what does the block have? The block has potential energy. So it has the potential energy of this much. So this is the height. And when the block comes to the bottom by the compressing the spring all the way down, it doesn't have potential energy. So all this potential energy is going to go to the spring energy, and there is no friction. So I'm going to say that I have a point A, I have a point B, and I have a point C. And I'm going to say that the potential energy gravitational at point A is going to the kinetic energy at point B, and that will go all to the potential energy of the spring at point C. So I have mgh is equal to, and I'm gonna convert it all to the spring because they don't ask me the velocity at point B. I can skip that middle guy out, take him out, and then what I have is the potential energy of the spring, which is 1/2 k and x squared. Also, the sine of theta, which is 30 degrees, is equal to h over x plus d. So h is equal to sine theta times x plus d. So I'm going to plug in my h instead of h into the formula. So what I have now is times both sides by 2. So I have 2, and then I have mg, and instead of h, I have this whole thing, which is sine theta, and then times by x plus d. And on the other side, I already times it by 2, got rid of the fractions. That is equal to kx squared. If I solve for x plus d, I have x plus d is equal to kx squared divided by 2mg sine theta. And from here, I have that the distance is equal to kx squared over 2mg sine theta minus x. So this will be my distance formula that it travels before it hits the spring. Now, if I plug in my numbers, I will have that the distance is equal to, and I got 1.4 centimeters or 0.014 meters. Here's another question that we're going to solve in this video. And a 10 kilogram block is released from point A. The track is frictionless except for the portion between point B and C, which has a length of 6 meters. The block travels down the track, hits the spring of force constant K, which is equal to 2,250 newtons per meter, and compresses the spring 0.3 meters from its equilibrium position before coming to rest momentarily. Determine the coefficient of friction between the block and the rough surface between B and C. As always, I'm going to start with what energy I have. So when the block is positioned above the ground, it has the potential energy. So all I have to start with the potential gravitational energy, which is equal to mgh. By the time the block gets to the bottom, it has some velocity. So it will have some kinetic energy. So some kinetic energy, and I'm going to call it just maximum kinetic energy. This kinetic energy is equal to the potential energy. So they're equal to each other because all the potential energy is going to go to the kinetic energy. Then there's going to be friction, frictional surface. So not all this energy that was here will go to the potential energy of the spring. That means I have to subtract the work done by the friction in this distance between B and C. And the rest of the kinetic energy, so I will still have some kinetic energy left, and the rest of this kinetic energy will go into the potential energy of the spring or maximum potential energy of the spring. I'm not just going to write maximum because that's going to be just the maximum. And so I don't really need this part, and I don't really need this part, because what I have is I start with the potential energy gravitational. Then I'm going to subtract, so from all that amount of energy, not all of it is going to go to the potential energy of the spring. I'm going to subtract the work done by the friction. And then the rest, what's left, is going to go to the potential energy of the spring. What is going to look like? It's going to look like this. I have mgh minus the work by friction. So when the block is on the surface, the forces that are acting on the block are mg and the normal force. And here, there is also going to be the friction force. So your normal force is equal to, your normal force is going to be equal to mg. So minus the work done by the friction. So it's the friction force, which is mu mg, times the distance. And the distance, I'm just going to call it d, distance between B and C. And the rest of it is going to be ending up in 1/2 k n x squared, the compression. So next, what I can do, I can multiply every single one of them by 2 and solve for mu. So I'm going to skim some steps, but you can go through the whole simplification. So I will have mu is equal to, if I times them all by 2, but every single term by 2, I have 2g mgh, 2 mgh minus kx squared divided by 2mgd. And if I plug in all the numbers that are given, I'm going to get coefficient of friction is equal to 0.331. Here's the next question we're looking at. A 3-kilogram block situated on the rough incline is connected to a spring of negligible mass, having a spring constant of 100 Newton per meter. The pulley is frictionless. The block is released from rest when the spring is unstretched. The block moves a distance of 20 centimeters down the incline before coming to rest. Find the coefficient of friction between the block and the incline. So I'm going to say that maybe the block was in different position because I need more space. So let's say the block was maybe at this height and will move all the way to the bottom. So it will move this much distance vertically, or this much distance along the incline. So this distance is by how much the spring is going to be stretched. So by this much distance, the spring is going to be stretched. The forces that are acting on the block are the normal force, mg, And that mg can be broken into mg cosine and mg sine from our dynamics lessons. So angle is going to be this angle, 30 degrees, and I have mg sine, mg cosine. Let me see which color is better. Maybe brown. So I have mg cosine and I have mg sine. Your normal force is going to be equal to mg cosine theta, or 30 degrees, or cosine theta. Okay, and now let's look at what is actually given at each point. So at this position, I have potential energy of the block, and then I lose all the potential energy. And there is friction force. There is friction force. So if there is friction force, then I'm going to say that the potential energy of the block, if there was no friction force, all this energy would go to the potential energy of the spring. So if I only had the gravitational potential energy, the block stretches, loses all the potential energy. That means all that energy must have gone into the spring energy. But there's friction, so I have to subtract the work done by the friction from the potential energy, and then the rest of it is going to go to the spring energy. So now I'm going to plug it in. I have mgh, then minus the force mu times n, which is mg cosine theta, and the distance it travels, d, and the rest is going to go to the energy of the spring, which is 1/2 k, and it's going to stretch the distance d squared. Also, h is equal to, let me choose this color, h is equal to d sine theta, d sine theta. So if I look at this triangle, I'm going to erase it after I'm done. So d, this one is theta, and this is h. So sine theta is equal to h over d. Then h is equal to d sine theta. So I'm going to replace my h with d sine theta and multiply them all by 2 to get rid of the fraction. So I have 2 mg d sine theta minus mu times 2, right? I have to multiply by 2. Mg cosine theta times d, and equals to kd squared. I see that every single one of these terms, so I have 1 term, 2 terms, 3 terms, every single one of them has d, so I can cancel d, and d. And I am solving for coefficient of friction, so I'm going to solve for mu now. Mu is equal to, I'm going to skip some steps again. So I'm going to move my mu term to the right and kd to the left, and then divide by wherever mu is standing with by. So I have 2 mg sine theta minus kd, and divide it all by 2 mg cosine theta. And I have the mass is given, the spring constant is given, the distance is given 20 centimeters or 0.2. If I plug in all these numbers, I'm going to get mu is equal to 0.19, and that is my answer for this question. Here might be our last video for this, our last question for this video. And I have a 20 kilogram block is connected to a 30 kilogram block by a string that passes over a frictionless pulley. The 30 kilogram block is connected to a spring that has negligible mass and a force constant of 250 newtons per meter as shown. The spring is unstretched when the system is as shown in the figure, and the incline is frictionless. The 20 kilogram block is pulled 20 centimeters down the incline, so that the 30 kilogram block is 40 centimeters above the floor and is released from rest. Find the speed of each block when the 30 kilogram block is 20 centimeters above the floor. That is when the spring is unstretched. So my measurements are not going to be up to scale. So I'm going to say that I'm going to stretch all this all the way till the end, just because it's easier. So I'm going to call this X. And when that is X, then my block 30 kilogram is going to go the same distance X up. So originally, I have the potential energy at this moment. There is a potential energy, mgh. H is 20. Then let me write it mgh as well. So let me do this in red, just because I want you to see why I'm going to do it, and then I'm going to erase this. So I start with let's stretch it first. So we stretch the block. The block 20 kilogram goes all the way down the incline. So what I have is the block 20 kilogram is not moving. There's no energy that the block of 20 kilogram has at the moment when I stretch the spring. What I have to start with is the potential energy of the block that is 30 kilogram. So let's call this one 1 and this one is 2. Also, when the block is back to this position, the original position, I'm going to call this one H. And H is equal to X sine theta. So if you look at this triangle, this is your H, this is X, this is theta. So sine theta is equal to H over X. H is equal to X sine theta. Now I'm going to write the energies I have before. So if I take the block M1 and I stretch it over here, so here is the block M1, then what energies do I have at this moment? Block 1 is not moving and it's not off the ground, so its potential energy is equal to 0. So block 1 does not have any energy, but block 2 does have energy. So the block 2, when it is stretched, it has potential energy of X, so it has M2GX. It also has the energy of this little H, so it has M2GH. And we also have the spring present, so we have the spring stretch, so that's 1/2 K, and I stretch it by X squared. And then after I release the block, and when it is back to the position where you see it in the picture, we have block 1 has potential energy. So the block 1 has M, potential energy of the block 1 is M1G, and H is equal to X sine, so that's X sine theta. Also, block 1 has kinetic energy, so I have 1/2 M1V squared. Block 2 has energy as well, so that's 1/2 M2V squared. And block 2 is still the height H above the ground in this picture that you see, so it has potential energy of M2G and that H, which is 20 centimeters. I see I have 20 centimeters MGH here and MGH over here. I can just subtract them from both sides to not make my equation more complicated than it should be. So I'm going to cancel this from the beginning. And also times them all by 2 because I don't want to have fractions. So I have 2 M2GX plus KX squared, because I times it by 2, equals to 2 M1GX sine theta. And when I times these two guys by 2, I also can take the V out, so plus V squared, and I have M1 plus M2. And I am solving for the speed of each block, so I need to solve for the velocity. If I solve for the velocity, I get the square root of, I have 2M2GX plus KX squared minus 2M1GX sine theta, and divide all of that by m1 plus m2, and my answer should be equal to 1.2 meters per second if you plug in all the numbers that are given in the problem. I will stop here because I don't think I have enough time to fit another 1 or 2 or 3 questions. So that will conclude our energy and work video number 5, and there should be another video number 6 coming after this. The problems should be easier in that video. This might be the most difficult questions, maybe 1 or 2 challenging in the other video. So I will see you in the next video.